I wanted to take a few minutes to discuss certain addition reactions that can be stereospecific. The first one is hydroboration. And you can see I've set up several examples here. And we know that hydroboration essentially adds OH and H in a syn fashion, syn addition. So essentially we're adding water across the double bond, and of course the unique feature of hydroboration is that it's anti-Markovnikov. The OH gets added to the less substituted carbon of the alkene. And because it's syn addition of the H and the OH, we can potentially get some stereospecific outcomes. So let's look at these three examples here. What we want to look at is, are there any stereocenters that are created as a result of this hydroboration reaction? And if I draw a generic product here, we see that the hydrogen here on the tertiary carbon does not generate a stereocenter, neither does the OH out on the primary carbon. So no stereocenters are generated. And so we don't have to worry about stereochemistry. So this would be an acceptable drawing of the product, and we can move on, go on to the next question. Let's make our alkene a little more complex and see what we get in that case. So here again we have the H on the more substituted carbon. We've got the OH on this secondary carbon now. Can you find any stereocenters in this product? Hopefully you identified one of them. This carbon is a stereocenter. And so here we have one chirality center formed. And in this case, we simply draw both enantiomers. It's not too complicated here. And so I would then draw the OH on a wedge, and I would draw the OH on a dash. We don't need to show this hydrogen being on a wedge or a dash because it's not on a stereocenter. It's not needed. You could show it, but it's not needed. And looking at the final example here, again, the OH goes on the less substituted carbon. The hydrogen is on the more substituted carbon. How many stereocenters can you find in this molecule? So here, we've created two new stereocenters. And of course, we know that a molecule that has two stereocenters can have potentially 2 to the 2, 4 stereoisomers. And here's where this discussion is important. This is a stereospecific reaction. It will not produce a random assortment of these 4 stereoisomers. Only certain ones will form. So what we want to do is use the syn addition to help us decide which of these stereoisomers that we want to draw. So we're going to make sure that our OH and our hydrogen are on the same side of the molecule, meaning they're both wedges or they're both dashes. So in this case, I've drawn both wedges. That is one potential stereoisomer. And the other one, of course, is the opposite, both dashes. So these, both enantiomers are formed. So that would be the proper product distribution for this reaction. And it's important to point out that the other stereoisomers, though, OH on a wedge, hydrogen on a dash, and vice versa, are not formed. This would be anti-addition of the H and the OH. So that's what we mean when we say that the hydroboration reaction can be stereospecific. In the case of two new stereocenters, it's important to remember that the H and the OH are added syn, so they either go on both on the top, like this one here, or both on the bottom, like the second example with with dashes. There's not going to be any sort of wedge and dash type stereochemistry. So we get 2 of the 4 potential stereoisomers when we have 2 stereocenters that are created. Let's look at this concept when we use hydrogen. And we know that hydrogen also proceeds via syn addition. And so generally I'm just going to draw the expected product and see what I get. In this case, I get a very simple alkane. There are no stereocenters, and so this is really the only product I need to draw. If we look at the second example, we get a molecule that looks like this. Do we create any stereocenters in this case? And indeed, this is a stereocenter. And so, of course, we know that the hydrogen can add to one or the other side. So we could just denote the product mixture like this, showing that we make a racemic mixture. I like to be a bit more specific if I can. So I'm going to put a wedge here. And I'm going to draw the same one with a dash to show I have a mixture of enantiomers here. And so again, we get to the last example. That's probably the most important one regarding the syn addition of hydrogen. So here's the expected product, and we've created, if I set this up right, 2 new stereocenters. And again, just like with hydroboration, I know that I have syn addition, so the 2 hydrogens should be added to the same face. So 2 new stereocenters could result in a total of 4 stereoisomers, but only 2 of them will form. So here I've added the hydrogen to the back side of the molecule, and if I just reverse those wedges into dashes, I get that. And I've added the hydrogen to the front side of the molecule. So these are the only 2 stereoisomers that will form when I have 2 new chirality centers that are formed. The other potential stereoisomers that have 1 wedge and 1 dash will not form. So that's stereospecific addition using the syn addition of hydrogen or hydroboration to generate some of the potential stereoisomers, but not all of them.